We ask all participants to keep the microphone off during the entire session to avoid interruptions. For our Zoom audience, in case of any inconvenience that may arise during the session, we ask that you send a direct message to the staff. If you would like to ask our guests a question, please send it as a direct message to Implex's staff. For those of you who are attending in person at the Congress Center, you may ask questions to our guests when indicated by the session moderator. The intention of this roundtable is to create a space for dialogue between the speakers and the audience, where we can express our opinions about various topics that are of relevance to our society. The topics that will be discussed in this session revolve around scientific denialism and disinformation, revolutions in physics, elusive theories, and paradoxes, among others. Depending on the development of this session is whether it will be possible to address the topics planned for today. We will now name the speakers who will make up today's roundtable, and we will give a brief introduction to each one of them. We remind you all that the panelists are also speakers at the International Symposium on Physics. We will be joined at this roundtable by Anthony Leggett, the John D. and Catherine T. MacArthur Professor and Center for Advanced Studies Professor of Physics at the University of Illinois, Urbana-Champaign. He is widely recognized as a leader in the theory of low temperature physics and has pioneering work on superfluidity that was recognized by the 2003 Nobel Prize in Physics. David Hughes, Director and Principal Investigator of the Large Millimeter Telescope, Alfonso Serrano. He's responsible for Laboratorio Nacional CONACYT of the Large Millimeter Telescope. He is the Vice President of the Governing Board of the Event Horizon Telescope and leader of the Mexican and Large Millimeter Telescope participation in the project. Douglas Nadelson, Professor and Chair of the Department of Physics and Astronomy at Rice University, with courtesy appointments in electrical and computer engineering and materials and science engineering. His research interests focus on condensed matter physics at the nanoscale, including atomic and molecular scale junctions, plasmonics, and nanodevices for the study of strongly correlated electronic materials. Daniel Oblak, Professor at the University of Calgary and Principal Investigator of the Quantum Cloud Laboratory. His research in communications and quantum networks has included implementation of quantum memory, photon sources and detectors, and optical to radio frequency transducers. In addition, today we are joined by Raúl Hernández Aranda as moderator of this roundtable. Professor Hernández is Associate Professor of Physics at the Department of Sciences, Tecnológico de Monterrey. His research areas include the characterization and generation of structured light, singular optics, optical coherence theory, and the applications into different areas of physical sciences. We will now turn the microphone over to Professor Raúl Hernández to begin the roundtable.
Okay. Well, thank you very much. First of all, I would like to thank all the speakers for your time, and just want to mention that this event is fully organized by students, so we are very proud of them. And well, thank you. Let's see how this discussion goes. The idea is just to have a very relaxed chat and try to give your best thoughts about these questions that I'm going to ask you. So, well, first of all, I would like to ask you probably something that is of interest for most of the students here. And the first question is, how do you choose to study physics? And for the order, I will just suggest to start probably with people that is here, and then we will move just around the clock. Okay, so we can probably start with David.
Hello, can you hear? Yes, okay. Well, thank you again for the invitation and to participate in this round table. And also let me acknowledge just how impressed I am about the organization of this event, the participation of all of you, the students here at Tec de Monterrey. It's clear to me that you have enormous confidence, initiative, enthusiasm, and interest in science. And so for me, it's a pleasure to be here and to engage with you both yesterday and hopefully more today. I'm an astronomer, an astrophysicist. I wouldn't class myself as a hardcore physicist. So I'll answer the question, how did I become an astronomer? I actually never had a telescope. I was not an amateur astronomer. I don't know the names of stars and constellations other than, the obvious ones. If it's a partially cloudy night, I can't go out and tell you because it's mid-May, it's 10 o'clock at night. I'm roughly looking in a particular direction that, those 3, 4, 10 bright stars, I can describe that. My interest in astronomy came through a single moment when I was 17. And I remember it so clearly. I was in a maths class, have been with the rest of my student colleagues, taking classes with this particular maths teacher for maybe 3 or 4 years during school. And we had been conducting or participating in course solving differential equations. And we have been doing exercises, for days and days and days and homework. And so the maths teacher, Mark Riddington, decided that, today we've done enough of that. Let me show you how you can apply differential equations, the knowledge you have, to actually solve some simple equations, the Lane-Emden equations, as I found out, that describe the structure of stars, that allow you to describe the temperature profile, the density profile, the pressure profile. Even talking about it right now, I still feel the same sensation, like the hairs on my arms, that, suddenly I was understanding, rather than calculating the speed the balls move down ramps and doing, simple sort of mechanical calculations, just abstract mathematical calculations, that there was this real link and something that just inspired me between maths, physics, astrophysics, understanding stars, understanding the universe. And so it was that moment that I just decided to go to the library, find a book. I lived in Lyme Regis, a small town. The idea that this small library actually had the one classical book on stellar formation, stellar evolution was, just the chances of that were small. And so I read that book, consumed it in a few days, and decided when I go to university, or that I want to go to university, first of all. No one in my family had ever been to university, so I want to go to university and I want to study astrophysics. So it was just because of that one class, that one maths teacher solving the Lane-Emden equations as a 17-year-old. It was amazing. And it's defined the rest of my life.
Yeah, well, it is. I can relate to that feeling of goosebumps. And I actually tell my students that I also have the same experience with some topics. Well, thank you very much for sharing your experience. We can move on to your answer.
All right.
Danny.
This is, yep, that's working. Okay. So yeah, funny enough, right? When I wasn't actually quite sure what I wanted to do with my life. And so, academia is kind of a good way to just keep sort of peddling water and not quite take a decision early on. But, if I talk about physics and science, why I went into that, my initial interest was actually also astrophysics. It was really what caught my eye. It's fascinating to see about stars and their evolution. I could sort of, tell everything about main sequence stars and how they evolved, and all my classmates in junior high school, they wanted me to tell them, and they probably just thought I was a freak, but anyway, it worked. And then I started university and went into the math and physics program, and it was a lot of math in the beginning and a little bit of physics, and then at some point you get exposed to a lot more that you didn't know about when you start university, and you're surrounded by a lot of other people who are really into it. In high school, physics and math was for about 2/3 of the people something that they just had to do and they would rather avoid. And so it was a really nice experience to come to a place where everybody was like really keen on everything. And then a turning point for me was also, an influence from a teacher, but that was more at the university. And that was my teacher in quantum mechanics. And this guy was colorful and enthusiastic, to say the least. And it just, laid it out beautifully. And I just thought, wow, this is so neat. And actually without too much math as well, because I'm not particularly good at math, but, that just like the simplicity of some of the results that you could get to was what really inspired me. And then, a little bit of random chance. There was a good research group at my university in quantum optics. I did my bachelor's with them. And so that's how, ended up with a master's and a PhD in that group. And that just, led me on that path to be in quantum, sort of quantum world. And I also found that, I love touching things and fiddling with equipment and do detective work around the lab. So I really enjoyed being able to touch and turn mirrors and plug things in and really work hands-on. And so I think, maybe some branches of astrophysics has that too, if you're working on telescopes and equipment, but that I found is really, really needed. I couldn't just be the person who sits and analyzes data all day long. That would not have worked for me.
Hopefully some of our students will find more motivation, because some of them are taking an experimental physics course this period. So, okay, well, thank you. It's very interesting. So we can probably continue with Tony Leggett, if you don't mind.
Yeah, sure. Well, I guess my path into physics was pretty unorthodox. I didn't start life on the science side at all. I was rather precocious, or rather ahead of my age in academic ability. And so basically at the age of 13, under the old British system, I had to choose between going into various streams at my school. And of these streams, the least prestigious, in those days, we're talking about the late 40s, early 50s, the last century, the least prestigious stream was science. The most prestigious one was classics, that is Greek and Latin languages and literature. And although my father was actually himself a science teacher, including physics, he basically raised no objections, in fact, rather encouraged me to go into the classics stream. And that's what I did. And so in high school, I got essentially, to all intents and purposes, I got no science whatever. I got some mathematics, and in particular, I got some informal modern mathematics, which was not part of my regular syllabus at all, but there was an old priest at my school who took me in hand and decided to teach me some modern mathematics. So when I went up to university, Oxford, I did what was the line of least resistance, basically, for someone who had studied classics at school. I took a particular degree at Oxford. This degree has a long name, which is Literae Humaniores. No one ever calls it that. They always call it Greats. And what you do in a Greats course is you study for the first 5 trimesters. You study classical languages and literature. And then for the last 7 trimesters, you study an equal mix of ancient history, ancient meaning Greek and Roman, and philosophy. But the philosophy is not Greek and Roman, it's modern. So it's much the same as the philosophy course you might get if you were majoring in it at some other university. Anyway, did that course. As I gradually came up towards it's a 4-year course, as I gradually came up towards the end of my 3rd year, I started really thinking about what I wanted to do with my life. And quite frankly, I was very immature and inexperienced, and it really didn't occur to me to do anything but go on into some kind of academic job, either at high school teaching or university. And since the subject in which I had been probably done best, and certainly the one which I'd enjoyed most of the three I'd studied was philosophy. I thought, well, I will go on and become a professional philosopher. And since, at least in those days, philosophy was not taught as a subject in high school in the UK, that meant I'd have to become a university philosopher. So yeah, sure. What I will do is I will go on, get a PhD, DPhil in philosophy, look for an academic job, and end up as a faculty member in some British university teaching philosophy. And somehow the more I thought about it, the more I realized I didn't really want to do that. So I started to ask myself, why? Why not? Why don't I want to become a professional philosopher? Well, I think had I had a bit more experience and been a little less mature, it might have occurred to me that maybe I shouldn't end up in academic life at all. I might have gone off and become a rock climbing instructor or something like that. But it didn't really. And so it had to be not something wrong with academia as such, but something wrong with philosophy. And gradually I came to sort of put my thoughts together and realize that what I didn't like about philosophy, at least as it was conducted in Oxford in those days, remember we're talking about the mid-50s, what I didn't like was that everything seemed to depend so much on your exact turn of words and your colleagues' opinions and so on and so forth. In other words, there didn't seem to be any kind of objective touchstone in that subject as to whether the work he was doing was good or bad or right or wrong. And somehow I started to feel instinctively that I wanted to work in a subject where there was going to be this kind of objective touchstone. Now, as I said, I had serendipitously had a very small amount of modern maths in high school. And so my first thought was to become a professional mathematician. And then I remember very clearly saying to myself, no, I don't want to become a professional mathematician. Why not? Well, here's exactly what I said to myself, as it were. Why not? Well, because in mathematics, if you're wrong, it means you're stupid. I would like to be able to be wrong without being stupid. And so I dismissed mathematics. Incidentally, I've had some pushback from professional mathematicians on that point. But anyway, that's what I thought at the time. And so, well, if it's not mathematics, then what was the next most objective subject? Well, at least what it seemed to be was physics. And so I decided that I did want to become a professional physicist. Now, the actual stages I had to go through in getting there, other than in themselves, this would be an hour's talk, so I won't try to bore you with that. But basically, that's how I got into physics.
Well, thank you. Very interesting road to physics. I do have some questions ahead regarding philosophy, so I'm expecting to the answers. Okay, well, let's continue with Douglas.
Thank you. And again, as others have said, thanks to the organizers, it's fantastic that students have done such a great job putting together this event. So my story is rather similar to Professor Oblak's. I grew up in Western Pennsylvania, and I went to a little public high school, and my father was an engineer. He was a nuclear engineer, actually. My mother was an English teacher, kind of a middle school, junior high school English teacher. And I sort of assumed I was going to do something related to math and science. I figured I'd probably do some kind of engineering. I mean, when I was really young, I totally wanted to be an astronaut. I was very into airplanes, space travel. It's, anything astro is still sort of my, my second favorite thing, if not my favorite thing. I remember very vividly being about 10 years old or so when the original version of Cosmos came out on public television with Carl Sagan, and you know, that I found that pretty transformative. So my high school had pretty poor physics instruction. I mean, kind of objectively bad physics instruction. My chemistry teacher was great, and I think he's never really forgiven me for going into physics in the long run and not being a chemist. So when I went to college, I was very, very lucky that I was able to get into Princeton, and I figured I would be an engineer. So but I had a pretty good math background, so I took the kind of the more advanced, mathematically advanced introductory sequence, and it was great. I really, really enjoyed it on the physics side, and I was taking the introductory engineering things as well. And I think the thing that really did it for me was in the spring of sophomore year, so second semester, my second year in college, I took an undergraduate, an intro quantum mechanics class from, as Professor Oblak said, you know, a colorful, very, very engaging teacher, and it really blew me away. And I started thinking that boy, you know, the physics aspects of this are frankly more interesting to me than some of the engineering aspects. I mean, I always find myself having to explain to current undergraduates, you know, the difference between engineering and physics in some sense is, you know, in physics or in the physical sciences, we're trying to find the rules that govern how the universe works. And in engineering, we're trying to leverage those rules to solve particular technical problems or societal problems. And of course, there's a big blurry line between those things. But I got, you know, basically sophomore year, I started really getting excited about physics, and I realized there was this engineering physics certificate program where it would allow me to take a bunch of physics classes and do some course substitutions so that I could basically sit on the fence for a really long time and not have to deal with the bureaucracy of actually changing my major, which would have been rather complicated by the time I was in my third year as an undergraduate. So that's what I did. And then when the time came to go to graduate school, or when I graduated, I had been fortunate. I'd done a couple of summers, or I'd done one summer where I did kind of a real engineering summer job at Westinghouse. And, you know, I kind of really got to see what really practicing engineering was like. And I enjoyed it, but it didn't really give me the same kind of spark of enthusiasm as the physics side. And also, like Professor Oblak, I like to actually do things with my hands and actually get my hands dirty in the lab. I very much like the puzzle solving detective work aspect where, you know, there's a very limited number of things you can actually measure in a lab. You have a limited set of tools, and you have to somehow come up with a scheme of inferring what's really going on under there and being able to test your hypotheses and rule out alternative explanations. I mean, I really like that stuff. So after years of sitting on the fence, I went to graduate school in physics, and that's kind of how I got into physics. In terms of condensed matter, again, I think I got into this partly because I kind of liked the scope and the scale. I liked the idea. The group I was in graduate school, you know, my supervisor was an old friend of Professor Leggett's, Doug Osheroff, and you know, his group was small. I mean, the typical author list on a paper was like 4 people. And I really liked that. I liked the scope. I liked the idea that you could have the experiment in a room. You could adjust everything, right? That appealed to me more than, you know, nuclear and particle physics, where I would have been one of 1,000 people as part of a giant collaboration. And I really liked the nuts and bolts aspect. And so that's kind of how I got into it.
Right. Well, thank you very much. Identifying some particular aspects that I also agree that encourage people to study physics or science, or particular, you know, some of them are related to the theoretical aspect and the enjoyment of you know, the intellectual work, but also, you know, hands-on experiences. So okay, well, let's move to the next question. There's this current idea of some physicists that physics is currently at a phase of stagnation. And I want to ask you if you agree with that, and what is your idea of the next revolution in physics that we can expect? I don't know now who would like to jump in to answer this question. Okay, Douglas, go ahead.
So this hits on something that has bothered me for many, many years, which is when people talk about a crisis in physics, what they're doing is they're using the word physics as an abbreviation for high energy physics theory. So it has annoyed me for a long time that the public perception of physics is very, very strongly, as a discipline as a whole, is very strongly driven by our nuclear and particle colleagues. And in particular, people have this idea that because experimental particle physics is very challenging, and they have not seen major violations of the standard model, they have not seen evidence for very exotic things like string theory and supersymmetry. Therefore, the entire discipline of physics is at a standstill. And that really frustrates me because, of course, there are parts of discipline of physics that are very much in an extremely exciting time. So condensed matter, I could talk at length about this. Atomic physics, people have new, in both condensed matter and atomic physics, people have new tools they never had before that are revealing all kinds of amazing, interesting things. There's stuff going on now that 5 years ago people wouldn't have dreamed that you would see some of the things we're seeing. The physics of living systems is a fascinating area where there's tremendous excitement and tremendous understanding, growth in understanding. Again, with new technical capabilities also on the experimental side. Astrophysics with the advent of gravitational wave observatories and things like the Event Horizon Telescope and the Atacama Large Millimeter Array and the observations about extrasolar planets, but also about neutron stars and black holes and compact objects. I mean, there's an enormous amount of fun and excitement going on in the discipline. And I think claiming that the entire discipline is at a crisis because there are not experimental violations, large-scale experimental violations of the standard model is really painting with far too broad a brush.
Okay. Well, anyone would like to
Sure.
add something?
I would agree completely with what Douglas has just said. And from the point of view of astrophysics, Douglas already mentioned a few of these facilities, but I would say that we are in this most amazing sweet spot, or about to start a few decades of enormous growth. Not to say that there is, the field is stagnated, but just an acceleration in the ability to understand the nature of the universe through these new generations of experiments at over a wide range of wavelengths. So over the next 10 years, we expect to see the start of huge radio arrays, the square kilometer array, which is a square kilometer of collecting area divided between South Africa and Australia, thousands of telescopes of different sizes, different technologies, studying the low frequency radio universe. We have proposals to build large arrays in the United States and northern Mexico at slightly higher frequencies that again will offer, using the same technique as we use with the Event Horizon Telescope, interferometry, to virtually connect these different telescopes and create images with enormous resolution. So, having huge eyes, sensitive eyes to again understand the universe. The ALMA telescope at millimeter wavelengths, the LMT is just starting its science case that all of you here have access to. And then, of course, the JWST has just been launched, which is the successor to the Hubble Space Telescope. And the United States and Europe and Asia are collaborating on building these huge optical telescopes, 30-meter, 40-meter class telescopes. So all of these telescopes are coming online at about the same time. And this hasn't happened for generations. There's maybe been one big observatory, that has sort of dominated advances in a particular science area. But now over the next decades, there's going to be this capability at all wavelengths to have this complementary data and understand everything from the formation of planets, formation of stars, formation of galaxies, more information about the origins of the universe. So I think it's an incredibly exciting time right now, both from the experimental side, and then obviously also motivates the development of simulations and theories with which you can test, or with which those observational data, will test and inform those particular models. So it's a very exciting time for the young generation of researchers getting into science, getting into physics, astrophysics right now. You basically have for the rest of your careers a really unique opportunity compared to the previous generations.
Okay. Tony, Daniel, I don't know if you would like to add something.
Oh, okay.
Yeah, sure. Go ahead.
Well,
Tony?
I too very much agree with what's been said, but I think I would look at it in some sense from a somewhat broader point of view. I don't know how many of you are familiar with the ideas which were primarily associated with the name of the late historian and philosopher of science, Thomas Kuhn, about normal and revolutionary science. Basically, Kuhn's thesis, at least in its most original and most sort of unredacted form, was that for any particular discipline, there are periods when basically the kinds of question you're allowed to ask, the kinds of answer you're allowed to give, and the sorts of evidence that you're allowed to adduce in favor of those answers, all of those things are pretty much agreed within the relevant community. And then these periods, this is what Kuhn calls normal science. These periods of normal science, according to Kuhn, are punctuated by episodes, often quite brief episodes in real life, where the so-called paradigm changes. That is, the kinds of question, answers, the evidence, etc., is all completely shaken up. An example of a paradigm shift, I think, in Kuhn's thinking, if I've got him right, would be the transition from classical to quantum mechanics. It wasn't so much that we had a different theory, it was simply that the kinds of question you were allowed to ask changed. In classical physics, the idea that you could not actually ask, why did this particular atom come out at this particular place on the screen or whatever, that would somehow be a meaningless question. That would have been totally alien to classical physics, whereas in quantum mechanics, the idea that you could not ask this kind of question would have been alien to classical physics, whereas of course in quantum physics it's essentially a given. So if we do look at things in those rather oversimplified terms, then I think I would tend to agree that we are in a what is basically a normal period of physics. It's not to say it's not exciting, and there are many exciting things that are going on, but the general paradigm framework is mostly fixed. It seems to me there may be an exception here, perhaps in cosmology, where people really do argue about whether it's meaningful to ask certain kinds of questions, but apart from that, I think we probably are in a period of normal science. Are we heading for a major revolution? I suspect yes. And the reason is that although we're making lots and lots of progress in all areas of physics, from condensed matter physics to cosmology, nevertheless, there's always some sense of rather slightly incremental progress, and underlying there are at least two, I think, real, well, I'm going to mix my metaphors. I'm going to say that underlying these success, there are two major elephants in the room. And one of those, sorry. One of these elephants in the room is the so-called quantum measurement problem or quantum realization problem. The fact that Crudely speaking, if you just take the formalism of quantum mechanics seriously, then things don't happen. There are different possibilities which are simultaneously realized. Whereas in, not just in classical physics, but in ordinary common sense, as it were, we take for granted that things do happen. Particular outcomes are realized. This particular electron came out on, registered itself on the screen at a particular point. It was not sort of diffusely spread over the whole screen. And there have been many attempts over the last 100 years or so to resolve this paradox, but I frankly don't think it's resolved at all. The second major unknown, which again, many physicists would regard as trivial, is the so-called arrow of time. Basically the fact that, at least in everyday life, we take it for granted that the past can cause the present and the present can cause the future, but not vice versa. Again, I don't think we really understand, despite the opinions of many distinguished people, and names of packed that we do. Personally, I have a hunch, and it's no more than a vague hunch, that the next really major revolution in physics is going to have something to do with our ideas about the arrow of time. And that when it does come, it will simultaneously cast our perception of the realization problem, the so-called measurement problem in quantum mechanics in a totally new light. But I mean, if you ask me, what is this revolution going to be like? There's a famous answer that was given by, I believe it's the famous jazz musician, I think Louis Armstrong, who was asked by a fan where jazz was going, and his reply was, well, man, if I knew where jazz was going, I would be there already. So that's my answer.
Yeah, well, okay. Well, thank you. It was a very interesting answer. Daniel?
Yeah, I'll take a slightly less philosophical and from a younger perspective, maybe. But one of the things that I would say we may be in a period of normal science, in that sense that we're not changing paradigms, but that normal science, the rate of discovery and the rate of transitioning actually really deep physics into real applications and things that matter in our real world is just accelerating quite drastically. So the rate of development of new ideas and just the expanse of research going on is much just I see growing. So you find real, from my field, quantum physics problems being relevant to more and more to everyday applications, which is really exciting. And another thing that I've sort of noticed over the last maybe couple of decades is that more and more of the world is also involved. So it's not a uniquely European or North American endeavor now, but you see new places in the world coming truly online. In some cases, starting to dominate science and physics over the older places in the world, the old world. So I think those are all exciting developments, and that point to, even normal science is a fascinating time to be in the physics field.
Well, okay, from this perspective, taking this idea of that we are probably in a period of normal science, then I have the question, so is there room for philosophy in science at this moment? And should we care about philosophy in science? Or what do you think? I don't know who I'm looking at someone, but probably, I don't know, someone who would like to share. Go ahead, please.
Yes, I think there is. In some sense, I think there's a place for philosophy everywhere, and in particular, everywhere in academia, because basically, independent of their technical views on, so let us say, free will or counterfactuals or whatever, I think philosophers have two things which they're always doing, which the rest of us don't do perhaps quite often enough. One of them is to ask, what do you mean? And the other is to ask, how do you know? I find, at least with quite a lot of my colleagues in physics, that, as I say, they don't stand back quite often enough and ask these two questions. And this can, and in fact, this can have some impact on the sort of nuts and bolts of unspectacular work, let us say, in condensed matter physics or particle physics, whatever. Because if you don't formulate your questions clearly enough, then you probably won't get the right answers to them. And if you don't, if you're not careful enough about the way in which you assess the evidence for what you believe, again, you're likely to go in completely the wrong direction. And I actually find it, this is perhaps slightly off the original question, but I think it's quite an important point to make. I have found quite frequently in my particular branch of physics, which is some areas of condensed matter physics, that you get a situation where a particular theory or a theoretical conjecture is put forward, and an experiment which is done, which brilliantly confirms it. And then thereafter, all the theorists, at least, and I was tempted to perhaps read more of the theoretical papers, all the theorists refer back to this original theory as if it is basically the foundation of the subject and can't be challenged. Meanwhile, the experimentalists, who in my experience tend to be more open-minded, go back, they do the experiments again and find that the first result was not right. That paper, I mean, the first paper probably got published in Nature or Science or whatever. The paper which finds different results will probably get published in a less so-called high-impact journal. And even after its publication, and even after the original people, in some cases, admit that they were wrong, people still quote the original paper as gospel. So I think one of the things I do think I owe to my training, my original training in philosophy, is to be able to stand back and ask these two questions. I think more specifically, when I was talking about topics which are, in some sense, at such a fundamental level as the quantum realization problem or the arrow of time, it is very useful to have a few philosophers in the room. What I found rather impressive is that when I was a student at Oxford in philosophy, way back in the late 1950s, none of the professional philosophers who were extremely distinguished lot, and they really were sort of international stars, none of them had any interest in physics or even in science generally. The very few that did were interested in rather dry subjects like what is the formal relation between thermodynamics and statistical mechanics and so forth, but none of them really got into the nitty-gritty of physics. They could trade arguments toe-to-toe with the professional physicists. That's completely changed. In fact, Oxford, ironically, is one of the major centres these days of what I would call philosophy of physics as distinct from philosophy of science. That is, investigation by philosophers or people trained in philosophy of real physics problems like the quantum realization problem and some of its ramifications. So yeah, I think we should by all means keep the philosophers in the room as far as we possibly can.
Okay, well, thank you. Just to see if we can probably make it on time and keep and just have some room for questions in the audience, I would like to ask the last question and see if you can also close with a piece of advice. The last question is, what are the challenges that you think science dissemination is facing right now? And if you have some piece of advice for the students that would like to pursue a career as professional scientists or physicists. I know who would like to start.
Sorry, so the question is, what is the value of
No, the challenges that the science dissemination faces today.
I mean, I think there are many.
Douglas.
Okay.
I think there are many challenges that science dissemination faces. You know, I never imagined that the internet would end up, you know, I thought, like many people, I thought, oh, this is fantastic. It's a way for, you know, it will revolutionize the world in the sense that no longer will it be impossible for individuals to influence large numbers of people without, you know, millions of dollars backing them or something like that. I thought the free flow of information would be a great thing. And unfortunately, like many, I didn't anticipate the fact that there is now an enormous dilute, you know, not so dilute gas of information and misinformation and disinformation. And I think it's very, very challenging to get accurate scientific information out there in the world and have it get the attention it deserves. And there are many factors on this. I mean, I think, you know, the idea that everything has to be encapsulated in 144 characters or in a 10-second soundbite, when in fact, things like the quantum realization problem are very complex, and it's hard to encapsulate them in 10 seconds. That doesn't mean they're not worth talking about, but I think to large portions of the general media, that's the attitude they take. I think it's very challenging to get, you know, there seems to be this decline among some people in the respect for actual expertise. So, you know, the idea that there's a perception by some people that if you're highly trained in an area, then it doesn't mean you're an expert. It means you've no objectivity because you have a vested interest of some kind. And I think that's very, very hard to fight against. I wish I had solutions for some of these things. I also think that more on the science publishing side, I think you know, Professor Leggett, I correctly identified, you know, some real challenges there too. I think there's this idea that somehow the ultimate prize is to get featured in a glossy magazine where you will end up there, you know, there's some percentage chance your work will be covered by the New York Times or something. But that's, you know, the issue about whether you're actually correct seems to take a back seat sometimes. And I think that, you know, there are some real challenges there too. I think there's hope. I think the advent of, you know, the rise of preprint servers and things like that really do enable people to reach larger audiences, and you kind of hope that in the end that in some self-organized way the discourse will favor actual empirical truth, and, you know, things that agree with observation and with experiment. But it's you know, there's a lot of noise out there in the communication side that's making this very challenging right now.
Well, I think that's a very good point. My concern is that sometimes we get dragged into discussions and arguments trying to counter some of the disinformation, and that sort of gives air and you know, oxygen to those arguments that somehow validates some of what they're saying, because this is now a professional dialogue, or at least it's a dialogue with professional scientists. And I worry that we find ourselves in this difficult situation of, on the one hand, wanting to respond and explain clearly why this information or disinformation is disinformation, why these are not correct theories, why these theories have been, or these ideas have been disproved, why we should no longer be talking about it. On the other hand, I think we as scientists have to do a much better job in continuously finding ways to promote the scientific ideals, the ethic, the idea of developing theories, developing experiments to test those theories, being open to different interpretations, just engaging with the public in different ways, and continuously trying to do that to promote science in many different directions, using many different opportunities. And in some ways, I don't like to use this word, but sort of to suffocate those efforts of people that try to put out controversial ideas just to be controversial, for self-publicity, for self-promotion. I think it is a difficult problem, as Douglas says, because of the internet, because of social media. It's so easy to put your own ideas out for your own purposes, and actually damage science, some of the scientific method and some of the scientific efforts that we go to as a scientific community.
Yeah, I do agree. We have a huge responsibility to build scientific literacy in the community, right?
So the whole area of outreach, I think, is an area for opportunity, particularly amongst the younger generation that are, for example, I have no social media pages. I don't have Twitter pages, Instagram pages, Facebook pages. You guys do, and those of you that are interested in promoting science and countering the disinformation have a huge responsibility as we move into the future.
Yeah, so I don't know if anyone else, Tony, Daniel.
Yeah, I would just say that I mean it's exciting, as everybody has said, with social media. You can reach a big audience, right? But the very short attention span that today you are aiming for when you're promoting things online, has to be in a few minutes. Like, I think 15 minutes is like as much as you can get people to possibly watch on YouTube, right? Anything. That means that, it gives this impression, it's exciting to be able to communicate and train yourself to communicate science in, somehow get a message out that clearly. But it does give that impression then to people that, well, it is a 15-minute job to actually understand it, where in reality, there's so much more behind it. And you have then, other people thinking that, if they spend an hour and then 15 minutes on making a video, their facts are as valid as yours. And I think there's a lot of debates that are scientific on very current, important events that are not necessarily in physics. But when I hear, trained people with the background talking about, medical issues, from my background as having gone through also the whole process of learning physics, I respect not the knowledge that I know that goes behind that, what is the depth of understanding that is required to correctly synthesize some knowledge down to, a 5-minute interview. And so I think that this is the good, a unique capability, a sort of experiential thing that you have from going through, almost any science degree that you can take to the world, and that you should respect, makes you able to respect knowledge in a more broader context. And you have to then, I think that's, what was pointed out, that you have to be out there on the barricades yourself, whether that's a virtual barricades or whatever, but a subset of you have to take that task seriously too, and promote the way that you can synthesize the facts that are true into the more general public, so that we don't, we are tending to get a little bit of those who are in the know and those who are not in the know, and those who feel like the whole world is too complicated for them. They tend to look at scientists as some sort of secret cabal of people trying to run the world for them, right? And it's a tricky problem how to I feel bridge that gap and make it not so that there are two classes of people, or that some people feel like they're out of the loop and will grab onto anything that just is going against the establishment for the sake of going against the establishment.
Okay, well, I don't know if Tony, do you have a final
I
word
don't
on
really
that?
think I have anything of substance to add to what's already been said. So
Yeah.
quite-
Okay. All right. Well, then we can open the session for questions from the audience. I don't know if we are also taking questions from the community that is. Okay. Yeah. So we.
Okay, thank you very much for sharing your. Sorry about that long walk, but thank you very much for sharing your ideas. Sure, okay, yeah, okay. And I was really wondering because a lot of us kind of complain about the education and the way physics and math is taught. And well, I think a lot of it is, you know, as the saying goes, the grass is always greener on the other side. But being really familiar with the A-level physics and the A-level mathematics and the Cambridge institutionalized exams, I saw that they really don't include any sort of the calculus needed. And that really affected me, well, entering university. And my physics professor really was not really happy about it, about the way they transformed things. But I'm not sure from your perspective, especially teaching at higher levels, if you think, like, how do you think the education of physics is being taken? If it's going towards a good path, or if it's getting a bit more leveled down without the mathematics? Because, well, I'm a bit biased because of the English curriculum, but I'm not sure if the US curriculum would be, or the SATs exams, which have also been a bit frowned upon for their multiple choice aspects. I'm not sure if I'm feeling a bit clear. It's kind of a bit nervous being here in front of really important physicists.
You're fine. Well, I would just say, unfortunately, my experience is that as time goes on, I find the entry level of students coming in, at least to my institute for the last 20 years, which is Inoi, in Tonantzintla, one of the Conoceet centers. The general level is going down to the point where we find ourselves in those sort of first many months actually having to teach, many basic concepts that in the past I would have expected to have been the responsibility at the, at the school level, or at least at the university level before even coming into sort of masters and PhD programs. And I think that's true. I haven't been in the UK for 22 years now, but my understanding is, talking to colleagues back in the UK university system, that it's a similar problem. Basically, you cannot get through the same amount of material in a 3 or a 4-year university degree course, because that first year is now doing a lot of what used to be the responsibility and the level that you would expect to leave the school level or education system at the school level with those basic skills. So I think it is a problem. It's not clear what the solution is, what even the cause of the problem is, other than overcrowding in schools, classes too big, not being able to push the brightest students, not being able, segregation is a horrible word to use, but for those that have the capability and the abilities to be pushed a little bit harder, I think that's an opportunity that's missed. But the education systems in many countries are really not enabling the very best students to really promote themselves and be pushed as hard as they possibly can. And I think you heard in in our introductory comments how, in all cases, individual teachers, individual professors were the sort of the spark, the inspiration for us to get into science and physics. And I think that's missing today in the sort of the lower levels of education. I don't know what the solution is.
We have some questions from our audience on Zoom.
Douglas has a comment.
Just very quickly. I mean, I think I agree with what you were just saying, broadly speaking. I think so. I've been very fortunate and privileged. Rice is a pretty, at the undergraduate level, we're a very elite institution in the sense that our acceptance rate is quite low. And what I've seen, I've been here 22 years now, and what I've seen is the best students are still fantastic. I do feel like there's been, the heterogeneity has grown. I think some of that has to do with also, Rice is trying very hard to try and provide academic opportunities to people from very diverse economic backgrounds, diverse social backgrounds. And it is just true that, people from the poorer segments of society, people from more rural areas, people, first generation college students, their level of preparation is not good. And it's hard for me to tell whether it's actually gotten worse or whether we're just, we're trying hard to admit more people from more diverse backgrounds. And that makes it very, very challenging. I mean, as something we've been wrestling with the entire time I've been chair with our undergraduate curriculum is, you want to still offer material so that the absolute tip-top students are challenged and that they will be prepared for the best graduate programs in the world, right? And I think we succeed at that. But at the same time, if that's your exclusive focus, then you've basically written off the people who are coming in with much less adequate preparation, and sort of determined that, okay, in an ordinary, time scale for a degree, they're never going to get there. And that's very, that's very, very, it's a very difficult choice. I mean, I think I too don't have a great solution to this challenge. I think I have a feeling like in the very long term that the advent of kind of, in some sense, AI-based teaching methods. I know this all sounds a bit like science fiction, but I think the long-term answer of online education is going to be me saying something like, hey Alexa, teach me multivariable calculus. And you could, I mean, individualized interactive tutoring aided by somehow highly knowledgeable artificial means might be a way to really bring the best education to the most people, but we're pretty far from that now. So I don't know what the short-term answer is.
Thank you very much.
Okay, so now we have some questions from our Zoom audience.
To Professor Leggett, do you have any opinion about some of the interpretations of quantum mechanics that have been proposed to solve the measurement problem, like Everett's many worlds interpretation, where there is no wave function collapse?
Yes, well, I do actually have a rather strong opinion about the so-called many worlds interpretation. When it is said by advocates, or typical advocates at least, of the many worlds interpretation, that the worlds which I or you at this particular time do not observe and could by construction never observe, when it's said that those worlds are, quote, equally real. I mean, those two words sound like English. What do they actually mean? I think that their words just floating completely free of any kind of context or meaning. So it's not that I think the many worlds interpretation is wrong. It could not even be wrong because it's simply meaningless.
Thank you very much, Dr. Leggett. We have another question here.
Yeah, thank you very much for the conversation we have here. I have a question, and considering the different areas we have here, quantum mechanics and everything we just heard yesterday and today, do you think physics or research involving physics somehow in the future will have a limit? I mean, whether we as a society choose the limit or natural processes choose the limit, do you think physics in the future, considering all the discoveries and the creations we've done in our whole history, do you think in the future we can have somehow a limit? I don't know if I was clear with the question. Thank you.
Well, let me give just a very simple answer. I mean, based on our experience so far, the experience of humanity as we've evolved to where we find ourselves today, I personally would like to say no. I don't think that we will find a limit. I think the imagination of us as as humanity will always be curious. We'll always be looking for new questions. We'll always be questioning what is put in front of us. We'll always be looking to understand in more and more detail the nature, the physical nature of the universe that we live in on all scales. And we have the ability, the creativity to continue to develop ideas, build experiments, to test those ideas. So I personally would like to say, I hope that we don't find some fundamental limit in our desire to understand and our ability to understand the universe. And again, as I say, on all scales, from the quantum level to the largest scales of the universe.
Yeah, go ahead, Dr. Late.
Yeah, I would just comment that there have been times in the history of physics, and certainly in the history of science generally, when a substantial body of the society has actually held that certain kinds of research should not be allowed or certainly not be encouraged, not because they're likely to give the wrong results, but because even if the results are right, they're liable to have undesirable social consequences. The obvious example one can think of from the history of physics, of course, is Galileo's telescope. The fact that at least some of Galileo's contemporaries refused to even look through his telescope, crudely speaking, because they thought that even if his ideas were true, they were likely to be socially very disruptive. Nowadays, you don't see that much in physics, but you do see it, for example, in certain areas like genetics, where people have quite seriously suggested that certain avenues of research should simply be blocked off. Again, because of the possible or allegedly undesirable social consequences of this. And I actually do wonder whether there may not also come a time again in physics itself where some kind of situation like that arises. So I think we ought at least to be on the lookout for it.
Thank you very much. We have one last question.
Okay, first of all, thank you all for accepting our invitation and for seeing us either virtually or in person. And my question is, what kind of metrics do you use to set up and determine whether you have achieved your group's goals? And what do you use, or how do you try to fight against the mentality of paperism?
Boy, that's challenging. I mean, I think that the thing that makes it very hard, as you already know, I think, because of the way you phrased the question, there are two things that make it very hard to really fight the idea of, when you say paperism, I think you mean, publication counting, citation counting, things like that. The one is, of course, that at least in the U.S. system, your ability to, as an experimentalist, your ability to keep doing work depends on getting funding. And very often the funding agencies actually practice paperism and they count publications and they care about impact citation impact. And the other is that if you want your students to do well and end up with, good careers, they kind of need to have demonstrated output and demonstrated achievement. And the easiest short form for that is papers, presentations, things like that. And, certainly there's not a one-to-one mapping between, the work that my group has done that has gotten the most citations and the stuff that I'm most proud of intellectually and the stuff that I'm most excited about. I mean, there's overlap. I don't want to make it sound like these are orthogonal things, but I don't have a great answer. You've correctly identified a major challenge though, right? I mean, you don't want to basically go into I don't think anyone is particularly motivated to go into this because what they really care about in the end is what their citation count is or their H index or something like that. I mean, at least God, I hope no one's going into this with that as their motivation.
Yeah, I could add that, I see universities trying and the society and funding agencies trying to involve other criteria. There's equity and diversity and inclusivity being counted when you apply for grants. And there's, also some more innovative aspects, like what is your impact on society? And it's all kind of nice, but there's a reason maybe why, this impact factor counting of papers was chosen it's just really simple, right? And the sad thing is that, all these other good metrics, it does, if you have to document it, which is a lot of the time the motivation behind, why do publications count? Well, it's because, that's how you get grants and that's how you get your position, that's how you get promoted. Well, then, this other criteria does add, just one more thing you have to track, one more thing you have to quantify. And that, although the intentions are good, and in principle it's good, it just becomes yet another thing. So somewhere one has to recognize also that there's, how do you make it not just more things to document, more things to keep track of when you try to, use these things or how leverage these things for doing your research. But then that's the one thing I think of it. Then it's like, well, how do you consider it a success, or how do you leverage your success to get funding and get your research group working? Another thing is just what are your internal values in your group and sort of what matters to you. There, I think you are, and that's a nice thing as an academic, you do have a lot of room to say that this is what I want from my group, given the external constraints of you have to publish some things once in a while, but the sort of internal dynamics, how you want to run, what do you consider success? Is it that the students, spend all their time in the lab, or is it that, they do some interesting stuff on the weekend and, they have a good time and they seem like they're happy and well rested, those are things that you can implement. And that's, one of the great things about, as I said, in being in academia is that you're running your own little shop to a large extent, at least if you're kind of in a smaller scale lab, then and you can really influence in that way a philosophy or sort of a mental picture of what your students will see as a good lab and a good working environment, how to work in science, and sort of put your little imprint on what becomes the norm of how you should run a lab that way, or research group. And I think that's one of the blessings of being in academia. You have that impact and the ability to shape future directions of other people that will go on to, some of them do great things too.
Let me just emphasize exactly that point. So yes, there are papers. Yes, there are citations. Here in Mexico, we also have to do an enormous amount of outreach and demonstrate that. And that's a worthwhile activity for the reasons that we discussed earlier. But it has to be counted, just like papers and citations, in many different formats. We have to demonstrate also, where we can, the value of the transfer of that knowledge to other sectors outside of our particular research interest, but the applicability of those results at the sort of level, the society level, and that those priorities, those demands are different in each country. But for me, just to echo Daniel's point, is one of the most rewarding things is not me counting papers or seeing citations or an H index, creep up slowly year by year, but it's actually being able to encourage and promote and support the student population and create or help contribute to the creation of the next generation of scientists that will perhaps take some of the examples that I try to provide on how to work, the work ethic, the ethics within science, how to communicate, how to collaborate across cultures, how to work with international colleagues. That's not always easy. We have different perspectives on how to live, how to work. I think being able to provide those examples for me, if I've done well, I would judge that as one of my goals, or that's how I would judge whether I've achieved one of my goals. Is a project successful? I would look at how I've been able to train and encourage the next generation, the formation of the next generation of students, the next generation of scientists.
Well, I don't know if Tony would like to add something.
Well, very, very, very briefly, I think the problem of having to always think, at least partly in terms of publications and high impact journals and so forth, is unfortunately a very real one. It seems inevitable. What I always tell my students and anyone else who wants to listen is, yeah, okay, you've got to do it. That's the way the world works. You are going to have to worry about whether the problem you're currently engaged in is likely to yield a natural science or PNAS publication within the next 2 years, which is when you're going to have to apply for your next job or next stage in your career. But always try, if you possibly can, to simply put aside some fraction of your time, maybe 20%, maybe 25, even 30% of your time, to think about problems which are so challenging that not only are you not confident of being able to solve them within 2 or 3 years, you're not confident that anyone will ever be able to solve them at all. Just devote a little of your time to that, and my instinct is that investment will really pay off.
Okay, yeah. Well, just as a final comment, I would like to thank all the speakers for your time, for sharing your experience, your perspectives with our academic community. I'm really appreciative of that, and it was really a pleasure for me to share this time and space with you. So I now turn the mic to you. Okay, well,
Yeah.
Thank you very much.
Thank you.
And
Thank you.
In addition,
Thank
we
you.
have a token of our appreciation we'd like to give you. Oh, go ahead. Tom. Okay. So we have something that we like to give our presenters, please. And if all of our presenters could stay online and here on the stage so we can take a picture afterwards with all the staff. We'd also like to take the opportunity to thank our sponsors, Turnium, Climate AI, and HEB. We thank everybody very much for your presence, and we want to remind you that there's going to be 2 workshops held at 2:30 p.m.
So we should standing up in front of the screen. Yeah. So we get everyone.
All right. Yeah.
Sign up.
I think Tony signed off. Thank you very much. Take care.
Thank you, Douglas.